Hello, welcome to Section 5, Concurrency and Grand Central Dispatch. In the previous section, we learned how to interoperate with other programming languages and add third-party libraries to our applications. In this section, we're going to learn about what concurrency is, and we'll learn how to manage our code using threads, operation queues, and Grand Central Dispatch. And now we move on to our first video of this section that introduces you to the concept of concurrency. In this video, we're going to take a look at how concurrency evolved from perceived parallelism to true concurrent parallelism. We're going to emphasize on learning concurrent programming as well as understanding thread management. Before we discuss how to manage our own concurrency, let's explore exactly what it is and why we need it. Concurrency is the process by which a computer or program can perform multiple tasks simultaneously. Consider the case of a computer with a single processor. In the 90s, all consumer-end computers had just one processor and could only execute one thread at a time. Even with just one core, we were able to run multiple applications in near parallel to each other by having the processor rapidly switch between each running process. Now, running each program for such short periods of time may seem terribly inefficient until you consider that modern processors can execute several billion instructions per second. So even if each program is only run for 1 millisecond, it can execute over 1 million instructions. As technology improved, chip manufacturers continued to release faster and faster single-core chips, which enhanced the perception of parallelism. Eventually, however, chip manufacturers hit a physical limitation on the possible clock speeds and ultimately compensated by releasing CPUs with multiple cores. Multiple processor cores means that the computer can execute multiple tasks at the same exact time. This means no more perceived parallelism. So, as programmers, we find ourselves in a multicore world, where even our smallest devices have multiple processor cores in them. In turn, most of the applications we use and create utilize multiple threads of execution. This allows our applications to remain responsive when performing time-consuming operations such as processing images, communicating with remote servers over a network, reading a large data set from a file, to name a few. So, what exactly are threads? A single application often has multiple paths of execution. These paths are known as threads. Each thread represents different computational tasks that are scheduled independently by the operating system. So threads are what allow our programs to perform several tasks at once. Once we queue a task on a thread, it is not immediately run, but rather it's scheduled to run by the operating system. So we have no guarantee as to when or in what order our tasks will actually run. It is important to understand that our program's threads are not isolated from one another. They share memory space, data sets, and even communicate directly with each other. Since there is no isolation between threads, this means that each thread is capable of interfering with the memory of other threads, allowing them to change the values before the tasks are completed. This can result in what's known as a race condition, which, as I'll demonstrate in the next video, is a condition where two or more threads are accessing the same data structures, resulting in undesired behavior. So, having said that, we must take care while managing our own threading. For more general information on concurrency, make sure to see this video's resource page, where I'll share some more insights and links to external resources. In this video, we saw how modern parallelism came to be and learned a bit about threads.